Okay, let's talk about something really interesting. It's called the halting problem, and it's a big deal in computer science. It might sound complicated, but it's really about a simple question. It's about knowing if a program will ever finish running, or if it will just keep going forever. Imagine you have a computer program, any program. Maybe it adds numbers, maybe it checks your email, or maybe it's something really complex. The big question is this: can we write a different program, a special one, that can look at any other program and tell us for sure if that program will eventually stop? Or if it will just run forever, stuck in an endless loop? The answer, and this is the important part, is no. We cannot. There is no such magic program. That's the halting problem. It's not that we haven't found it yet. It's that it's fundamentally impossible to create. And this is a really important idea. It tells us about the basic limits of what computers can do. Let's break it down a bit. What is a program, anyway? Well, a program is just a set of instructions. Think of it like a recipe. You follow the steps, one after another, to bake a cake. A computer program is the same. It follows steps to do a task. You give it some ingredients, some input, and it crunches away, following its instructions. Eventually, if everything goes right, it gives you a result, like a baked cake, or a number, or a picture on your screen. That's a program that halts. It finishes, it stops, but what if a program has a mistake? Or what if it's designed in a way that it never gets to the end of its instructions? Imagine a recipe that says, mix these ingredients, then go to step 3, then go to step 2. Step 2 says, mix some more ingredients, then go to step 3. And step 3 says, add more flour, then go to step 2. You would just keep going back and forth between step 2 and step 3. You'd never get to bake the cake. You'd just be mixing forever. That's an infinite loop. The program never halts. It just runs and runs and runs. We see this sometimes in real life. Your computer might freeze. A program might become unresponsive. Sometimes that's because it's caught in an infinite loop. It's just doing the same thing over and over with no way out. It never finishes its job. It never gives you a result. It just keeps trying to process stuck. Now, a lot of the time we can tell if a program will halt. If you write a simple program that adds 2 numbers and then prints the result, you know it will stop. It has a clear start and a clear end. If you see a program that says, do this forever, well, you know that one won't stop. We can often figure it out for specific programs, but the halting problem isn't about a program. It's about any program. It asks if we can build one super program, let's call it the Halting Oracle, that can take any other program you can imagine and any input that program might use, and then tell you with 100% certainty if that other program will halt or not. This Halting Oracle would be like a crystal ball for computer programs. Why would we want such a thing? Oh, it would be incredibly useful. Think about it. Software companies spend huge amounts of time and money trying to find bugs. There are bugs that can make a program crash, or freeze, or get stuck in an infinite loop. If we had a halting oracle, we could feed every new program into it. It would tell us if our program was guaranteed to finish, or if there was some path, some input that would make it run forever. Imagine self-driving cars, or medical equipment, or financial trading systems. You absolutely need those programs to finish their tasks. You can't have them getting stuck. A halting oracle would be a lifesaver. It could prevent countless crashes, save endless debugging hours, and make software much more reliable. It sounds like something out of science fiction. It would solve a huge problem in computer science. But here's the kicker. Even though it would be amazingly useful, it just can't exist. And this isn't just a guess. It's been proven. It's a mathematical proof. And the proof is really clever. It uses a trick called proof by contradiction. Here's how proof by contradiction works. You want to show that something doesn't exist, so you start by pretending it does exist. You say, okay, let's just imagine for a second that this magical thing is real. Then, you follow the logical steps that would come from that assumption. If, at the end of all those steps, you find yourself in a situation that makes absolutely no sense, a complete contradiction, then your initial assumption must have been wrong. That means the magical thing you imagine can't possibly exist. So, let's try it with our halting oracle. We want to prove it doesn't exist. So let's pretend it does exist. Let's call this imaginary program H each. It never makes a mistake. It works for every program and every input. That's our assumption. Now we're going to build a brand new program. We'll call this tricky new program contradiction maker. This contradiction maker program is designed specifically to mess with our perfect halting oracle, Leish. Here's how contradiction maker works. Contradiction maker takes just one input. And that input is itself a program. Let's call the program it takes as input punchest. So contradiction maker asks, hey, H. If I run porn test and give porn test as its own input, will porn test halt? This is important. The input to launch pentest, pentua test. The program is pentua test, and the input to that program is also pentua test. It will just spin forever, doing nothing useful. If hash says no portest loops forever when given portest as input, then contradiction maker will immediately halt. It will just stop right there. So, to recap contradiction maker, it takes a program puntest. It asks hash what pointer test does when given pointer test as input. If hash says pointer test halts, contradiction maker loops forever. If HS says porn test loops forever, contradiction maker halts. This contradiction maker program is a bit strange, but it's a perfectly valid program. It has clear instructions. It's well defined. We could, in theory, write it if H existed. Now for the final mind-bending step. What happens if we feed contradiction maker itself as input? So we run contradiction maker, contradiction maker. Let's think about this carefully. When we run contradiction maker, contradiction maker, contradiction maker follows its instructions. The first thing it does is ask, hey, what happens if I run contradiction maker and you have contradiction maker as its own input? Will it halt? A possibility one. Let's say our perfect halting Oracle H tells us, yes, contradiction maker will halt when giving contradiction maker as input. If HS says that, then according to the rules of contradiction maker, because H said contradiction maker halts, contradiction maker must enter an infinite loop. But wait, if contradiction maker enters an infinite loop, then it doesn't halt. So, Lahash said it halts, but it actually loops forever. This is a contradiction. Lahash made a mistake. But H is supposed to be perfect. Possibility 2, let's say our perfect halting Oracle H tells us, no, contradiction maker will loop forever when given contradiction maker as input. If Hatch says that, then according to the rules of contradiction maker, because Hatch said contradiction maker loops forever, contradiction maker must immediately halt. But wait, if contradiction maker immediately halts, then it doesn't loop forever. So, H said it loops forever, but it actually halts. This is also a contradiction. H made a mistake. But H is supposed to be perfect. In both cases, no matter what our perfect halting Oracle H says, we end up with a contradiction. Lacha is forced to give a wrong answer, but Hatch was assumed to be perfect. This means our initial assumption that such a perfect halting Oracle Lacha could exist must be false. Therefore, no such program hash can exist. There is no general program that can reliably tell us if any other program, given any input, will eventually halt or run forever. This is the halting problem, and why it can't be solved. It's a bit like those old paradoxes, like the barber in a town who shaves everyone who doesn't shave themselves, who shaves the barber. If he shaves himself, he breaks his rule. If he doesn't shave himself, then he must shave himself, according to his rule. It's a logical knot that can't be untangled. The contradiction maker program creates a similar logical knot for the halting oracle. Now, it's important to understand what this proof does not mean. It does not mean we can never know if a specific program will halt. For many, many programs, it's pretty clear. We can look at the code, we can run it. We can test it, and we can say, yep, this one stops, or nope, this one looks like it's going to loop. What it means is that we cannot write one single program that can take absolutely any possible program as input and always give us the right answer. We can build tools that try to find infinite loops. We have things called static analysis tools that look at your code without running it, trying to spot problems. Debuggers can pause a program and let you step through it, hoping to catch it if it gets stuck. These tools are really helpful. They can catch a lot of common errors, but these tools are not perfect. They cannot be perfect. They might give you a warning about a loop that actually does stop under certain conditions. Or, more dangerously, they might miss a loop that actually would run forever, because the halting problem proves that they cannot reliably catch every single one for every possible program. They are approximations. They are best effort attempts. They are not the universal perfect halting oracle. This fundamental limit was first shown by a brilliant mathematician named Alan Turing in 1936. This was even before modern computers existed. He was thinking about the very nature of computation itself. He imagined a theoretical machine now called a Turing machine, which is a simple mathematical model of a computer. And he proved, using a similar contradiction, that even this ideal machine couldn't solve the halting problem. His work laid the foundation for computer science. It showed us what was possible and what was not possible for any kind of computer. The halting problem has big implications. It means there are fundamental limits to what we can automate. We can't just write a program to solve every problem for us. Some problems are simply undecidable. That's the term computer scientists use. The halting problem is the most famous undekittable problem. It also means that programmers can't rely on a magic program to check all their code for them. They still need to think carefully. They need to design their programs well. They need to test thoroughly. They need to understand the logic. It's a constant challenge to make sure programs do what they're supposed to do and actually finish. Think about software verification. This is about trying to mathematically prove that a program does what it's supposed to do and nothing else. It's a very hard field. And the halting problem shows why it's so hard. You can't just write a program that takes another program and verifies it automatically for all possible properties, including whether it halts. It's a complex, human-intensive effort, so we live with the halting problem. It's a basic truth about computation. It means we can't create a program that can unfailingly predict the behavior of all other programs. This doesn't make computers less amazing. In fact, it makes them even more interesting. It defines the boundaries of their power. It shows that even with all their speed and complexity, there are some logical hurdles they simply cannot overcome universally. Programmers learn about this early on. It shapes how they think about writing code. They know they can't rely on a black box to tell them if their program will ever get stuck. They have to build in safeguards. They have to think about edge cases. They have to consider what happens if input is unexpected. They have to be careful when designing loops. It also means that there will always be a need for human intelligence in understanding and creating software. We can automate many things, but we can't fully automate the task of proving that all software behaves perfectly under all conditions. The ingenuity of a human programmer, the careful thought that goes into designing robust systems remains essential. The halting problem is a cornerstone of theoretical computer science. It's not just a puzzle. It's a deep insight into the nature of algorithms and computation itself. It tells us that some questions, simple as they might seem, have no universal algorithmic answer. It's a powerful reminder of the limits and therefore the precise nature of what computers truly are. They are incredibly powerful tools for solving defined problems, but they aren't all-knowing or infinitely capable. And understanding that limit is just as important as understanding their vast potential.